Hello friends, welcome back. In this session of heat transfer subject, today we are going to learn black body radiation. My name is Mr. S.V. Kumbha, Assistant Professor, Sharad Institute of Technology, College of Engineering, Yetra, Ichalkarji. In previous video lecture, we have learnt related to radiation, the basic concepts related to radiation, the wavelength, that is electromagnetic waves, etc. So, first we will discuss related to black body radiation. A black body is an ideal emitter. For example, a black hole. So, imaginary one. So, energy emitted by any real surface is less than what is emitted by a black body. Now, consider two bodies. One is completely black, and second is any color body. So, the energy emitted by a real surface of any object will be lesser than the heat emitted by a black body. So there are some assumptions involved in it. First assumption, it is related to it is an ideal emitter, means at every frequency it emits as much as energy or more energy than any other body at the same temperature. So in introductory lecture we have studied heat will be rejected only when there is a temperature difference, right? So this black body radiation, as it is a completely emitter, ideal emitter, so it emits radiation at every frequency. It emits as much as high than at any other range and at the same temperature. The temperature must be same. The temperature of black body and the temperature of any real body must be same. Second assumption is related to diffuse emitter. So black body radiation is a diffuse emitter, that is the energy is radiated isotropically independent of any direction. Isotropic material is that material in which thermal conductivity remains same in all the direction. It means that it will radiate heat energy equally in all the direction. The monochromatic emissive power E lambda can be defined as the rate per unit area at which surface emits thermal radiation at a particular wavelength lambda, and a black body has the highest value of E lambda, that is monochromatic emissive power, at any given wavelength. So Planck's criteria for perfect black body. So first criteria, allow radiation to enter but not reflect. So if you have learnt one black hole experiment or black hole assumption in physics, so a circular part is there and there is one aperture, so radiation will enter but we will not allow it to reflect back or transmit. So that is the first criteria, Planck's criteria, which is related to perfectly black body. It will absorb all the possible radiation but it will not reflect any kind of radiation. Second assumption is related to it possesses a minimum thickness adequate to absorb the incident radiation and prevent its re-emission. As I had already told you that it will absorb all the incident possible radiation and it will prevent its re-emission. Third, it satisfies severe limitations upon scattering to prevent radiation from entering and bouncing back out. So emissivity, the ratio of emissive power of a body to emissive power of a completely black body at the same temperature is called as emissivity of that particular body. So emissivity epsilon is equal to E upon E lambda, where emissivity depends on temperature, wavelength and surface smoothness. For a completely black body, emissivity of completely black body is equal to 1. In most solids and liquid, the radiation emitted from interior are absorbed by the adjacent molecule thus making it a surface phenomenon. But in case of gases and semi-transparent solids, radiation is a volumetric phenomenon. Radiation laws. So, first law of radiation is Planck's radiation law, which governs the intensity of radiation emitted by unit surface area into a fixed direction from black body as a function of wavelength for a fixed temperature. So, E lambda, which is a function of lambda, is equal to 1 upon lambda raised to 5 into 1 upon lambda square minus 1. C1 and C2, these are the constant, which is nothing but C1 is equal to hc square and C2 is equal to hc upon k. Stefan-Boltzmann law. This is second law which is related to radiation. The total energy radiated per unit surface area of a black body across all wavelength per unit time, which is also known as the black body radiant excitance or emissive power. Emissive power of a black body is directly proportional to the fourth power of its absolute temperature. So EB is equal to EB is directly proportional to T raised to 4. In order to remove that proportionality sign, we have to add one proportionality constant, that is sigma, and sigma is known as Stefan-Boltzmann constant, and that Stefan-Boltzmann constant value, standard value, is 5.67 into 10 raised to minus 8. For a real body, epsilon is equal to E upon EB, which is less than E, right? So for a real body, E real body is equal to epsilon into sigma into T raised to 4, where epsilon is the emissivity of that particular object. So for any real body, E is equal to epsilon into sigma into T raised to 4. Wien's displacement law. This is third law which is related to radiation. The black body radiation curve for different temperature peaks at a wavelength inversely proportional to the temperature. So one graph is shown. Spectral energy density, that is kilojoule per meter cube minute with respect to its wavelength. So there are certain curves which are shown there at 3500 Kelvin, 4000 Kelvin, 4500 Kelvin, 5000 Kelvin and 5500 Kelvin. So here there is a different temperature peaks at wavelength, and that will be proportional to, inversely proportional to the temperature. Therefore, the product of lambda max and temperature remain always constant. So T absolute in Kelvin and lambda max, it might be nanometer or meter, which is equal to constant, and that C is known as Rayleigh's-Jeans approximation, and that value coming to be 2.89 into 10 raised to minus 3. Kirchhoff's law of heat radiation, which is the fourth law of heat radiation. For a body of any arbitrary material emitting and absorbing thermal electromagnetic radiation at every wavelength in thermodynamic equilibrium, it is the ratio of its emissive power to absorptive power, and which is equal to universal function only of radiative wavelength and temperature. That universal function describes the perfectly black body emissive power. So an arbitrary body emitting and absorbing thermal radiation in thermodynamic equilibrium, the emissivity is equal to absorptivity. So epsilon lambda is equal to alpha lambda. So such bodies do not occur in physical reality. So Kirchhoff's law can be written as correlation between spectral emissivity and spectral absorptivity. So epsilon into lambda, alpha lambda into lambda, which is nothing but epsilon into which is equal to alpha. All calorimetry based on hemispherical emissivity calculation are based on this particular Kirchhoff's law. Gray and diffuse body. A source with low emissivity, that is emissivity is greater than 1, independent of wavelength of light, often as referred as gray body. All gray bodies will have emissive and absorptive power less than that of black body. Diffuse emitter is a surface for which the intensity of emitted radiation is independent of direction. The diffuse gray body approximation of real bodies make their otherwise complex study and analysis simple. Radiation intensity. So intensity I of radiation at any lambda is defined as the rate at which a radiant energy is emitted in theta and psi direction per unit its small area, that is normal area, per unit solid angle per unit wavelength. Radiosity. Total radiation leaving a surface due to reflection and emission. So J is nothing but radiosity, which is equal to epsilon into EB plus rho into G. And for an opaque object, J is equal to epsilon into EB plus 1 minus alpha into G. But according to Kirchhoff's law, alpha is equal to epsilon, that is absorptivity is nothing but emissivity. So putting the value of alpha as epsilon, we get J is equal to epsilon EB plus 1 minus epsilon G. On solving this, we can get value for J. Hemispherical black surface emission. Now, if we consider an imaginary enclosure of hemispherical surface, then for hemispherical black surface emission, IB is equal to EB upon pi, that is sigma T raised to 4 upon pi. This is hemispherical black surface emission. So radiation exchange between the surfaces. So some assumptions are there. Surfaces are separated by non-participating medium. This is the first assumption. Second assumption, it will not emit, absorb or scatter radiation. And for that purpose, one factor, that is view factor, is included. The view factor F suffix I to J is defined as the fraction of radiation leaving at which it is intercepted by jth surface. So reciprocity theorem says that Fij into Ai is equal to Fji into A into suffix J. So this is the radiative heat exchange between surfaces. Rate of heat transfer into surface from A to B or from B to A. So Q A emitted is equal to epsilon A into sigma A. On solving, we will get QB is equal to QB absorbed minus QB emitted. So for this video lecture, thank you very much.